Hi everyone and welcome back to part 9 of classical linear regression model. So if you are someone who is following my econometrics playlist, you will know I have covered classical linear regression model in details. I have started with the assumption. I have gone into parameter estimation of this model. Also, I have proved the blue properties of alpha and beta. And finally, I have shown you how to test the hypothesis in the context of classical linear regression model. So today we'll be starting off with something called the heteroscedasticity. That is going to be the first violation of the assumption of classical linear regression model. So if you're new to my channel, so please brush up the assumption video. You have to see the assumption video first in order to understand these lectures. In the subsequent lectures, I'll be covering how the violations of the assumption of CLRM model affects the result that we are going to infer from our model, right? So in this video, I'll cover the basic concept of heteroscedasticity. What is heteroscedasticity? I'll give you an example. I'll also explain with the help of residual plot. And in the later part of the video, I'll go into the consequences of heteroscedasticity. If heteroscedasticity is present in your model, how will that affect the overall result of your model? That I'll explain in details. And in the next video, that is going to be part 2 of heteroscedasticity, I'll go into the detection method of heteroscedasticity and also what are the tests or what are the remedial measures that you can use in order to avoid this problem, right? So this is what is the agenda of today's video. So let us see what is heteroscedasticity. Now, if you see this word, this is a very heavy word. If someone is new to heteroscedasticity, please understand it is made up of two words. First word is hetero. First word is hetero. Hetero means unequal. The word hetero means unequal and the word scedasticity means variation. Variation, or you can call this as dispersion. In statistical term, we call it dispersion. So heteroscedasticity means unequal variation or unequal dispersion. Now, if you know the assumption of homoscedasticity that I have explained in my assumptions video of CLRM, you will know what is homoscedasticity. According to classical linear regression model, the error variance, that is this variance of this epsilon I term given the xi values, this has to be a constant. This has to be a constant for all the observations that we take into account. And this is the assumption of homoscedasticity. Let me call it homo. Homo means equal. Homo means equal. So if you vary the value of x, x1, x2 up to xn, whatever be the values of xi, the variance of the error term is always taken to be a constant, which is denoted as sigma square. This was the case in homoscedasticity. This has to follow in order to maintain the CLRM assumptions, right? Now, if what happens if we violate this assumption? Violate means this assumption is not holding basically. So see here, this is the violation. If variance of epsilon I given xi is not equals to sigma square, in other words, we can write it will be equals to sigma I square. Instead of only sigma square is a constant. If you write this to be equals to sigma I square for all I, where I is varying from 1 to n, suppose you have n observations, then see if whenever you change your observation, if I take I equals to 1, it will be sigma 1 square. If you change I to 2, it will be sigma 2 square, where sigma 1 square and sigma 2 square are not equal. So as soon as you put this suffix here, I, this will mean that this variance is not constant. This is not constant. So if it is not constant, which means error variance are unequal. So mathematically, this is the explanation of heteroscedasticity. Now look at this definition in the context of CLRM. Heteroscedasticity refers to violation of the assumption that variance of the error terms will remain constant across observation. I hope this is now clear. Mathematically, this is what is heteroscedasticity. Given the non-stochastic xi values, the error variance will not be constant. It will vary with the value of xi. Where these are usual things, epsilon I at the error term, xi is the independent variable and sigma square will represent the variance, right? So up till this much, I hope this is clear. Now let us take the help of an example to explain this concept, what this actually means. Suppose we consider this simple linear regression model in this fashion. This is the simple two-variable regression model that we work with. Now, what happens is that suppose this yi is the dependent variable, which is the household expenditure. Suppose, for example, we are denoting this yi variable as the household expenditure, and this xi is the independent variable, which is household income. So what this model says is that your household expenditure will be dependent on the household income. That is the simple model, and epsilon I is the error. Now, what will happen in the homoscedasticity context and the heteroscedasticity context? Let us see. First, we have the homoscedasticity. In homoscedasticity, this is the mathematical derivation. But what this actually means is that suppose a person earns 10,000 rupees a month. This is the income of the household. Whether a person earns 10,000 rupees a month or a person earns 1 lakh rupees a month, what happens? The variability in how much it will deviate, the expenditure deviates from the expected expenditure will be similar. Suppose you are earning 10,000 rupees a month and your monthly expenditure is 5,000 rupees. Suppose what happens now, your monthly in hand increases, you are earning 1 lakh a month. Then also your expected expenditure will not be that different from 5,000 rupees. This is what this assumption means. The expected value, this is your expected expenditure. Your expected expenditure will not increase even if you change the value of xi. Xi, see, here I have defined xi to be the household income. Household income. So suppose you are the only person in your household. So if your monthly in hand is 10,000 rupees, your expected expenditure is 5,000. Even if your monthly income goes up to 1 lakh rupees, then also what happens? Your expected expenditure is more or less the same. It could be 6,000. It could be 7,000, but it cannot be 20,000 or cannot be 50,000 and so. So this kind of dispersion is not allowed in case of homoscedasticity basically. And by this example, you can understand that it is a very unrealistic situation. When your monthly in hand increases, you should, spend more amount, right, to improve your lifestyle. So this is an absurd situation. So homoscedasticity cannot capture this kind of a model. That is why the violation is required. That is why violation is required to model the actual realistic situation. Now you can give this a read. This means that the spread of error remains uniform across various income levels under homoscedasticity basically. This is under homoscedasticity. So what happens if the error term has a constant variance, then for any level of income, xi, any level, xi could be 10,000, xi could be 1 lakh, any level of xi, the deviation of yi from the regression line will remain roughly the same. So regression line means the predicted values basically. So error term or the residual is what? Residual is yi minus yi cap. This I have explained you previously. So the actual value of yi and the expected or the predicted value of yi, this deviation will give you the residual. That is why residual plot is helpful in order to, see or detect heteroscedasticity. That I'll come in a while. But if this deviation is zero, basically, if deviation is very small or this deviation is roughly the same for all I, this deviation is roughly the same for all I, then you will say it is the homoscedasticity case. That is what is written. For any level of income xi, the deviation of yi from the regression line. Regression line means basically yi cap values will remain roughly the same. This means that whether a person earns 10,000 or 1 lakh per month, the variability in how much they deviate from their expected expenditure is similar, right? So the deviation has a fixed range. It will deviate in some particular fashion. That will be a constant. That will be a constant, which is sigma square. So this will what happen if the CLRM assumption is not violated, that is homoscedasticity is met. Now let us come to heteroscedasticity, hetero. Let me call it hetero. So in this case, what happens? Suppose the variability of household expenditure increases as the income increases. So variance of epsilon I is increasing as xi is increasing. If this is the case, or it is decreasing as xi is decreasing. If this is the case, then we will say it is the case of heteroscedasticity. In this case, low income households have small predictable expenditures while high income households exhibit wider range of spending behavior. So we know this, right? That if you are low income household, suppose your monthly earning is only 15,000 rupees, right? If your earnings are only 15,000 rupees, then most of your earnings will go into food and your rent, right? Then you will spend most of your income in food cost or your rent cost. That is what will happen. So you have, for lower income household, the expenditure are small and predictable. It is predictable that you will firstly allocate your income to fulfill your basic needs, that is food, shelter, clothing, etc., etc. So your expenditure will be predictable depending on the income range. Now, if you are belonging to high income range, suppose you are monthly earning 1 lakh rupees, monthly if you are earning 1 lakh rupees, then your expenditure is not predictable. It is unpredictable. Here, what happens as your income increases, XI increases, your variability in spending also increases. Your variability in spending also increases. Suppose you are, so this food and rent cost is easily satisfied with this 1 lakh income. The rest of the income you can allocate to different streams. You can invest in something. You can invest in real estate. You can invest in stocks and bonds, etc., etc. Or you can, buy luxury goods and all. So the rest of the money that you have, the idle money that you have in your hand, can be spent on anything that you wish, right? That can be spent on anything that you wish, and that spending is not predictable. That spending is not predictable, and hence the variability is very. I hope I am making this concept clear. If you have any questions, you can let me know in the comment section. I'll reply to that. Right? So if you can take this example just to let your concept be absolutely clear. So if you have higher income, then as your income is high, you can spend a higher portion of your income into unpredictable things that I as an individual cannot say what you will do with that unpredictable or that idle amount of, right. So that spending will be unpredictable, or you could, instead of spending, you could aggressively save that amount. That could also happen. Suppose you want to buy a house 5 years down the line, then you could aggressively save that extra amount also, so that you can make the down payment of your house. So that can also happen. So that's a personal choice. That's a personal choice, whether you will spend that additional amount, or you will save that additional amount, or you will invest that additional amount. That is not predictable. That is the thing that I want to explain, right? So see here, in this case, low income households have small predictable expenditures, while high income households exhibit wider range of spending behaviors. And that is why what happens, variance of epsilon I given this xi values, xi here are the earnings, will be sigma I square. I, where sigma I square increases with xi values. And this will be the violation. So we are not satisfying this homoscedasticity assumption of CLRM, and we are violating this assumption. And that is the first violation, that assumption that constant variance of CLRM is not holding. And that will be the concept of heteroscedasticity. I hope this is absolutely clear. Now let us see this residual plot in order to explain this in a much better fashion. This is something called the residual plot. Residual plot. Here on the y-axis, what do you have? Residual. This is epsilon I cap. Residual. So this is basically yi minus yi cap. Right? I have given you the difference between error and residual in the first class itself. So if you haven't seen those videos, you can check that out, right? So here, how do you detect heteroscedasticity? See this first diagram, first residual plot. Here you have x side, here you have income, your monthly income. Suppose this is your monthly income. So what you see here is that as your monthly income increases, 20 to 40, 60, 80, suppose this is in thousands, assume that. So 20,000, 40,000, 60,000, 80,000, 100,000. So if this happens, as your income increases, you see the residuals are uniformly spread across this line. This is the zero line. This is the zero line, means there is no deviation in the actual spending and the predicted spending, right? If this is the case, then there is no heteroscedasticity. There is no deviation basically. Now, what happens in case of homoscedasticity is that the deviation is uniformly spread. See, these represents the deviation. This represents the deviation. The deviations are uniformly spread across these two halves. Above this line and below this line, this blue cross, basically, these blue crosses are uniformly spread. You cannot say in this half, in this particular half, there are more deviations. In this half, there is less deviation. You cannot say that, right? So in both the halves, what we see is that constant variance is seen. Constant variance. So you can see that the deviation will range from this point to this point, basically. Plus 20 to minus 20. There is a particular range. Plus 20 to minus 20. So in this particular range, the entire deviation is lying, and also that are uniformly distributed. These deviations are uniform, or these residuals are uniformly distributed across these two halves, and that will give you the visual detection of homoscedasticity. Now come to heteroscedasticity. Here what you see, this is the zero line. There is no difference in actual and predicted value of household expenditure. Now what do you see? Whenever you see a funnel shaped, see, this is a funnel shape, this kind of a diagram, this kind of a structure. Here you don't have the funnel shape, right? In the left-hand panel, you don't have any kind of funnel shape. But here what happens? As your income increases from 20 to 40 to 60 to 80 to 100, as your income increases, see, the deviation also increases. The deviation also increases. In the lower income level, this is the deviation. This is the range of deviation, basically. This is the range of deviation. As you keep on increasing your monthly income, see, here the deviation is much more than this particular line. So this will give you a funnel shape. The deviation is increasing. The deviation is not constant. It is increasing along with your monthly income. So that is the visual detection of heteroscedasticity. Again, for some example, what could happen? Suppose this is the case. This can also be a funnel diagram. Initially, the deviation must be, for some other example, initially the deviation is very high, but after a certain point, the deviation is low. This could also happen. This is also a case of heteroscedasticity. So this is how you visually detect. If you have a funnel shape like this or a funnel shape like this, you will say there is heteroscedasticity. But from this kind of a scenario where your deviations or your residuals are uniformly spread across these two halves, you can visually say that there is no deviation or unequal deviation present. So it is the case of heteroscedasticity. The error variance is constant throughout. Right? I hope this is absolutely clear. And here you have explanation of this diagram. Two scattered plots illustrating homoscedasticity, heteroscedasticity. So in the left plot, you have homoscedasticity that is being shown in this blue, these residuals are shown in blue. So the residuals of the errors are evenly spread across all income levels. This satisfies the CLRM assumption that error variance is constant. Whereas the right-hand plot here, this is the right-hand plot in red. In right-hand plot, what you see is that the residual shows increasing variance as its income increases, forming a funnel shape. So funnel-shaped residual plot is an indication of heteroscedasticity, and this violates the CLRM assumption, leading to inefficient OLS estimates. So this is the concept of heteroscedasticity. Now in the next place, we'll look at the consequences. If heteroscedasticity is present in your model, what will be the consequences and how will that affect the properties that we have initially discussed? Okay, so let us start with that. The first consequence will be OLS estimators remains unbiased. Even if heteroscedasticity is present in your model, we can say the estimated value of beta are still centered around the true values. Now let me show you how to derive this property. Let us go one by one. Proof of unbiasedness under heteroscedasticity. Suppose your model is like this. Yi is beta xi plus ui. I am not considering the intercept here, but even if you consider it, there will be no problem. I is 1, 2, up to n. This is the regression model, simple two variable regression model. Here, we assume that variance of ui, okay, let me call it epsilon I. In all the previous cases, I have called this epsilon I. Let me call it epsilon I. It doesn't matter. It is sigma I square for all I. So this is basically a heteroscedasticity assumption. Heteroscedasticity is holding. Now what will you do? You find out the residual sum of square. The process remains the same. Summation I from 1 to n epsilon I cap square. This will be summation I from 1 to n. And now what will you do? You will minimize this residual sum of square with respect to beta cap. So for that, what do? You have to find out the normal equation. The normal equation is del beta cap Now, if you take the partial derivative, you will have 2 summation I from 1 to m yi minus beta cap xi minus beta cap equals to 0. So this 2 and minus will go out. You will have, okay, sorry for this. This will be xi. We are taking the derivative with respect to beta. Sorry, this will be minus xi. Yeah. Now what you can do, summation I from 1 to n. This will be xi yi. And here you have beta cap. Summation I from 1 to n xi square. So what you can do? So beta cap will be simply summation xi yi upon summation I from 1 to n xi squared. Now what can you do? This replace this yi value here. Let me do it in the next page. Beta cap is summation I from 1 to n xi. Instead of yi, write beta xi plus epsilon I upon summation xi square. Now, if you multiply summation I from 1 to n, this beta will come out. This will be xi square plus summation I from 1 to n xi epsilon I. So this will be simply beta plus this summation xi square will go out. This will be summation I from 1 to n xi epsilon I xi square. So this is what is beta cap. Now, if you take expectation on both sides, this will be beta plus summation I from 1 to n xi expectation of epsilon I upon summation I from 1 to n epsilon I squared. What will happen? This expectation of epsilon I, this is simply 0. This property is not changing. We are only changing the variance property, but the expectation of epsilon I is still 0. And that will give you expectation of beta cap simply equals to beta. So if this thing is 0, the entire portion is 0. And multiplying 0 with this thing. And that is how you prove the unbiasedness property. So under heteroscedasticity, still beta cap is the unbiased estimator of beta. So unbiasedness property is not changing, and that is the first consequence. OLS estimators remains unbiased, and this is how you prove it. You can take the intercept also, and then also this will be the case. Now the second and the most crucial thing is that this is the main consequence that OLS estimator will be inefficient now. It will not be blue, which means that the variance that you will find out, the variance of beta that you will find out will not be the minimum variance, as we have proved in the Homoscedasticity case, variance of beta cap is the blue estimator of beta, that is, it is unbiased and it has the minimum variance. But here, if heteroscedasticity is present, then the variance that you will find out will not be the minimum variance, which is a bad news, obviously. The OLS estimators will still give the correct on average, that is, we have proved in unbiasedness, but they vary more than necessary across the sample. So now we will prove the inefficiency property of the estimator beta cap. Let us see how you will do it. Variance of beta cap minus beta. Okay. This will be expected value of beta cap minus beta whole square. Now, what is beta cap minus beta? From this particular thing, beta cap minus beta is this second term. So write that summation I from 1 to n. This. Now expectation will be only on the random variable and all the non-stochastic parts will come out, this whole square. Expectation is on only this thing. Now what you will do, variance of beta cap. The first part remains the same. How do you expand the second portion? Summation I from 1 to n xi squared epsilon I squared double summation I naught equals to j xi xj epsilon I epsilon j. This is the usual process that we follow. If you are following my video for quite a time, you will know this. So here what happens? Summation I from 1 to n xi squared expectation of epsilon I squared, and this portion will be 0 because non-autocorrelation property is satisfied. Let me write sigma I square and expectation of epsilon I epsilon j is still 0. We are not violating. Non-autocorrelation assumption is still intact. So variance of beta cap is simply I from 1 to n xi square whole square. And here what do you have? Summation I from 1 to n xi squared sigma I squared. So this will be the variance of the beta cap estimator under heteroscedasticity, which is strictly greater than the OLS estimator. If you remember, this was the OLS. This was the OLS estimator or the variance of beta cap under OLS. And this is strictly greater than this particular estimator. So this has proved us that the variance will be inefficient. So OLS estimators will be inefficient, they will be not good, since the variance that we will calculate is strictly greater than what we have got in OLS method. And since we have proved that OLS method, under OLS method, the variance is the minimum, so this will be not the minimum variance. So inefficiency is present under heteroscedasticity. Now let us see the other consequences. So this consequence is one of the basic consequences which is very intuitive because standard errors are incorrect. Standard errors are just the square root of variance. So we have just proved that variance will be inflated. So standard errors also will be inflated and it cannot give you the correct standard errors. So that is the third consequence. The standard errors are incorrect, bias in the variance estimation. Standard formula for calculating standard errors in OLS assumes homoscedasticity. If heteroscedasticity is present, this will be either too large or it will be too small. In general, we see that the standard errors are too large. So if you have large standard errors, you can, by looking at the figure, you can say that yes, heteroscedasticity might be present in your model. And what are the implications? If standard errors are underestimated, hypothesis test becomes too optimistic, because T statistic is what? T statistic is beta cap upon standard error of beta cap. So if this figure is large, if this standard error is very large, altogether this T statistic will be lower, right? So this could be one thing, or it could be overestimated. Hypothesis testing could become too sensitive and we might fail to reject the null hypothesis. So there is a possibility of both type 1 error and type 2 error if heteroscedasticity is present in your model. And it is obviously a bad news, because hypothesis testing and confidence interval will lose their reliability due to miscalculated standard error. If your calculated or computed statistic itself is not right, then the hypothesis testing or confidence interval that you will find out depending on this T statistic will also be incorrect, and this will give you miscalculated standard error and misleading results altogether. So this is the third consequence. The fourth consequence is also very obvious. As I have told you, the T statistic and the P values will become unreliable. T statistic is beta cap upon standard error of beta cap. If standard error of beta cap is not properly calculated, T statistic will also be not proper. Also, the P value, which is the probability of obtaining the test statistic as extreme as observed, that will also get affected. And what could be the consequences for that? If standard errors are underestimated, T statistics appear larger than they should be, leading to false statistical significance. Or if the standard errors are overestimated, T statistic will appear smaller. As I have told you, if the standard error is large, then overall this T statistic will be smaller. And if this standard error is lower, then overall this T statistic will be inflated. So depending on the nature of the standard error, T statistic will also be either inflated or it will look very small. It will not be a proper T statistic. So it is also bad news, because we cannot trust the results that we have obtained in hypothesis testing, which might also lead to wrong policy and business decisions. So heteroscedasticity, if present, you have to remove it before working with the model. Now also the confidence interval. The confidence interval will be misleading, because as I have told you, as I have derived this thing, what is the confidence interval of beta and what is the confidence interval of alpha. Confidence interval also depends on the standard error. So if the standard error and the T statistic is not proper, then the confidence interval either will be too wide or it will be too narrow. That will be the problem. That will be the consequence. Suppose this is the proper standard confidence interval for beta cap, or beta, sorry, for beta. This is the proper standard error. Either if heteroscedasticity is present, either it could be too large. When standard error is higher, when standard error is too high, either it will be a widened confidence interval, or it could be a too narrow a confidence interval. So see, too narrow, if the standard errors are underestimated, the interval will be too narrow, like this, overconfident conclusions. And if it is too wide, if this happens, if it is too wide, that is standard errors are overestimated and unnecessarily cautious conclusions. So it is also bad news, because we get misleading conclusions about the precision of our estimate. So if confidence interval is not correctly estimated, then the precision of the estimates will be distorted. So in order to have precision in your model, confidence interval also needs to be correctly estimated. So these are all interconnected, right? If your variance is not properly estimated, your standard error is not properly estimated. If standard error is misleading, then your hypothesis testing will be invalid. And also, standard error, will affect the confidence interval in your analysis. So these are all things are interconnected. The only severe consequence that you have to remember is the inefficiency of the estimates. That is, variance will be either too small or too large, and it will be not proper. And everything else follows from that inefficiency itself, right? The last two consequences. Fifth consequence is the prediction error becomes unreliable. This is also the same thing, that if heteroscedasticity is severe, prediction, if your model itself is wrong, misleading, then the predictions that you will make from that model will also be misleading. It will be less reliable, and the variance in prediction will increase, meaning some predictions will have much larger uncertainty than others. It is also a bad news, because prediction for high variance observation might be inaccurate. And there is one seventh consequence, which says incorrect model specification. It says that if heteroscedasticity arises due to misspecification of model. Misspecification is a separate chapter in econometrics that I'll cover in details in future. So as of now, understand if there is some misspecification, if your model is not correctly, specified in the initial place, then what will happen? It could be due to missing variables or incorrect functional form. Then the regression model might not correctly capture the relationship in the data. If ignored, this can lead to misleading economic and business insight. So model might need modifications to fix this problem. So this is one of the methods of fixing the problem of heteroscedasticity that I'll come to in my next video. So let us summarize everything that we have learned today. We have understood what is the concept of heteroscedasticity, and these are the list of consequences. So this is all in one place. You can take a screenshot. You can remember this in this particular fashion. These are all the possible consequences of heteroscedasticity, and this is the explanation why this is happening. OLS remains unbiased because the estimated coefficients are still correctly estimated and the population parameters. OLS becomes inefficient because the variance of OLS estimated is large than necessary. Standard errors are biased, leading to incorrect statistical inference. T-statistic p-values are unreliable. This will give you incorrect hypothesis testing results. Confidence intervals are distorted. It can be either too wide or it could be too narrow. It will be not proper. Prediction errors will be unreliable because model predictions have large uncertainties. And finally, possible model misspecification indicates missing variables and wrong functional. So this is what I wanted to discuss for today. In the next video, I'll go into the goal-filled quant test and all the other tests that you can use for, testing heteroscedasticity, and all the remedial measures will also be explained in the next video. So do not miss the next video. That will be a very important video in order to understand this concept. So thank you so much for your time. I hope you find this video helpful. If you do, then like this video and please subscribe to my channel in Economist. I continue making these useful videos for you. And this is absolutely free for you, but this will give me immense motivation to continue making such things for you, right? So please subscribe to this channel and let me see you in the next video. Thank you for your